All right, y'all. So this is the chemistry SL paper 1A, B, and 2. It was our mid-year with everything that we have learned thus far. So without further ado, let's jump right in. Starting with question 1 of paper 1A. What are the units of molar mass? Molar mass is just grams per mole or gram mole 1 inverse. Which information does the empirical formula provide? I don't know what happened with my font there, but empirical formula is just the simplest ratio of atoms in a molecule. These are all memorization thus far. All right, first time we have to think, what is the molecular formula of a compound with an empirical formula of CHO2 and a relative molecular mass of 90? Well, the empirical mass is 12 plus 1 plus 32. That 32 comes from the 16 of each oxygen times 2, which is a total mass of about 45. If the molecular mass is 90, we multiply by 2, therefore we're multiplying that by 2, so it's C2H2O4. Moving on to number 3, which gases are acidic? So when we look at these, we can kind of think about it a little bit in terms of like atmospheric conditions, which sometimes help. Nitrogen dioxide and sulfur dioxide can both be attributed to acid rain, so they got to be acidic. And if you know much about the ocean, carbon dioxide is what's causing ocean acidification. So we have 1, 2, and 3, all of those. What is the maximum number of electrons in energy level n equals 4? Well, in n equals 4, we have all s, p, d, and f orbitals. S can hold 2. There are 3 p orbitals, each holding 2 for a total of 6. There are 5 p orbitals, each holding 2 for a total of 10. There are 14 f orbitals, each hold, or sorry, 7 f orbitals, each holding a total of 2, which adds to 14. 14 plus 6 is 20, plus 10 is 30, plus 2 is 32 electrons. Which of the following is electron configuration of a metallic element? Well, when we look at our periodic table and we look at our block system, this is our S, this is our D, down here is our F, and over here is our P block. P's are mostly non-metal. Things that end in S and D are usually metal. Actually always metal except for hydrogen and helium. So we're just going to look for something that ends in the D block or the S block. So no, no, no. Oh, it has to be C. All right, there it is. Speaking of, what is the correct labeling of the box of periodic table? Well, it is D. I just did that above. All right, number 8. What can be deduced from the period number of an element? So when we look at the period number, that is the row it's in. So it's these horizontal columns or rows of our periodic table. And so when we're looking at the periodic table, looking at the uh, period, we generally know the highest occupied energy level because it's either 1, 2, 3, 4, 5, 6, or 7. So that tells us that. We do know the number of sublevels in the outer shell because in period 4, we technically have 4s. We have 4s, p, d, and f orbitals that exist, but it doesn't say occupied. It just says number of sublevels. So we have that. We do not know the number of outer electrons. We need the group for that. So the families, group 1, 2, 13, all the way to 18. So it's going to be 1 and 2 only, A. Moving to number 9. I think our answers got shifted. I don't know why that happened. How many electrons will be gained or lost when an element with the electron configuration 1s2, 2s2, 2p3 forms an ionic bond? Well, 1s2, 2s2, 2p3. Looking at the valence shell, that's energy level n equals 2, I see that we have 2s electrons plus 3p electrons for a total of 5 valence electrons. It's going to add 3 electrons to get to 8, the magic number for an octet. So we'll gain 3 electrons. So 3 electrons gained right here. Number 10, which substance is likely to have an ionic lattice structure at 298 and 100 kPa? So for something that has an ionic lattice structure, we're looking for something that's ionic at room temperature and pressure. So an ionic compound, generally I think of something like salt, specifically table salt, NaCl, and I think about that. So does salt have a melting point that's high or low? Well, salt's melting point is pretty high. It doesn't melt readily. And when you melt it, it's not conductive. So when it's in its liquid state, it's still not going to conduct electricity. It doesn't have free electrons, unlike metals. So it's going to be no. So C. Why does the melting point of the elements decrease down group 1? Well, as we go down group 1, we do have an atomic mass increase, the number of electrons does increase, the radius increases, and the ionization decreases. That's all true. But melting is when the elements start losing that strong bond they have next to each other and they start breaking down into looser combination of elements that flow past each other. And what has the greatest effect on that attractive force is the radius, because the further the atoms' nucleuses are from one another, the less attractive force they have with each adjacent atom's electrons. That's what's holding them together. And they don't have that anymore when you make it larger, because this is all back to electrostatic interactions. And as the distance increases, the force decreases. So as the distance between the atoms increase because of a radius increase, that attractive force decreases. In which molecule does the central atom have an incomplete octet? When you see incomplete octet, look for boron. It's always boron. Boron only has BF3, looks like this, with no valence electrons up here. It's kind of just like a blank spot up here. And so it only has 6 valence electrons when it's full in boron trifluoride. All right, number 13. Which allotrope, oxygen or ozone, has a stronger bond between oxygen atoms, which absorbs a higher frequency UV radiation in the atmosphere? So the stronger bond is going to imply that it's more stable. And when you think about oxygen ozone, well, when we had the ozone hole in the ozone layer forming, it wasn't the hole in the oxygen layer. Ozone was what was decomposing. And because ozone's decomposing or more readily decomposes than oxygen, we know oxygen has the stronger bond. So the stronger bond is going to be in oxygen. Furthermore, if we're looking at very specifically, ozone looks like this with a single bond and a double bond, and it creates what we call resonance structures. So either of these two bonds can be the single or the double. And we actually have two weaker bonds than just a regular double bond, which is incredibly strong. So ozone is going to have the weaker bond. Now, which absorbs higher frequency UV? That's ozone. That's what's the cause for the ozone layer degradation. Or sorry, that's what our ozone layer does. It absorbs the high frequency UV and helps keep us safe as humans down on Earth. 14. What is the enthalpy data of combustion? Sorry, what is the enthalpy of combustion of propane 1-ol in kilojoules per mole according to the following calorimetry data? So this calorimetry data says they took some propane 1-ol and uh, they burned it. I'm trying to draw it. That's not a fire. So here is our propane 1-ol, and they burned it in there. And that burning heated this water. And so what we're trying to do is find out how much energy got conveyed to that water from the propane 1-ol. So we're going to be just using Q equals mc delta T. So the mass of the water is 75. The specific heat capacity is 4.2. The temperature change is 24 degrees Celsius or 24 Kelvin, doesn't really matter. So that's going to give us our Q. Now that went into water, so it's positive. Therefore, if this has a positive Q, that left propanol, so it's a negative Q. So now we're looking for negative 75 times 4.2 times 24. That is the amount of joules. But we want kilojoules, so we have to divide by 1,000. That's going to turn it into kilojoules. We also have to divide by the moles. So if we want per mole, I'll write that in green, mole, then we have to also divide by our mole, so 0.015. So this is the answer we're looking for. So that answer provides us with D. Negative 75 times 4.2 times 24 divided by 0.015 times 1,000. All right, 15, again, we got one that got split. Which diagram shows the enthalpy change for dissolving X, or dissolving solid X in water if the temperature of the solution decreases? So if the solution temperature decreases, then that means the compounds absorbed that energy. That means they absorbed energy. Therefore, it is a positive delta H. In other words, endothermic. Here's a positive delta H, endothermic. 16. What is represented by the dotted line on the enthalpy profile? Oh no, my enthalpy profile got cut off. It's okay, we can just redraw it. So this is the reaction we have, and this is our dotted line. This is our reactants, and this is our products. And so this dotted line shows a lower activation energy. Therefore, we must have used a catalyst because a catalyst provides an alternative pathway for reaction and therefore lowers the activation energy. All right, 17. What happens to the average kinetic energy of the particles of gas when the absolute temperature is doubled? Well, temperature is just average KE. So if we have 2 times the temperature, we have 2 times the average kinetic energy. So we're increasing by a factor of 2. That's it. Which value of the reaction quotient Q shows the lowest relative amount of products at a particular point in time? All right, so for this one, we have to remember that Q shows us our products over our reactants, generally. The concentration of products over reactants. So what we're looking for is if we have the lowest amounts of reactants, if this bottom number is low, then Q should be high. So what we're trying to find is a reaction quotient that shows the highest possible Q for this reaction. Sorry, I actually said this backwards. Lowest amount of products. Whoops. So if our products are low, our Q is also low. Whoops, my mistake. Therefore, we're looking for the lowest Q value, which is right here, 4.9 times 10 to the negative third. All right, another shifted graph. Which products are formed by the neutralization of nitric acid and calcium hydroxide? So if we look at nitric acid, HNO3 plus CaOH2. Well, this is an acid plus a base, so we're just going to get water and a salt, CaNO3, water and calcium nitrate. I won't even balance the equation because I know that our answer doesn't have it balanced either. All right, which combination describes a strong bronzed-Lowry acid? So an acid donates a proton. So a strong acid would be a good proton donor. Therefore, if it's a very strong acid, it's going to be very weak base. And our answer is B. All right, that's paper 1. Paper 2, we got a little cut off there, but a student investigates the effect of exposure of air on the ascorbic acid, vitamin C concentration on a specific orange juice. Equal volumes of the orange juice are sealed in identical flasks and placed in the refrigerator for 2 weeks. Samples in the refrigerator are exposed to air by removing the stopper for a different number of hours each day as shown. So Identify two variables that are controlled. Anything that stays the same. The stopper is the same for each. The flasks, the type of orange juice, the amount of orange juice, the fridge is the same. The temperature of that fridge is the same. Uh, the amount of time in fridge is the same. It's all the same. Those are all controlled variables. The concentration of ascorbic acid is determined by titration with a standard iodine solution. Every few days, 10 centimeters cubed of orange juice is removed from each sample, diluted to 100 centimeters, and titrated. So generally, we dilute it so we can notice a change better. So what I mean by that is we use a lower concentration iodine as well, lower concentration of iodine. And because we're dealing with lower concentrations, we can get a more exact uh, volume added. And so we can be more accurate. And we can control moles added. It's a lot easier to control the amount going in when each drop is 0.0001 milliliters versus 1 milliliter. If we're adding less at a time, we're far more exact. Furthermore, just a point of order in this, orange juice is opaque, so when we dilute it, we can notice a color change better. So we can notice a color change better. There are a lot of reasons to do this. Identify possible systematic error with the method regarding the sample that is exposed for 0 hours. Well, we don't want them to expose to air, and yet there's some air right there. So even the one that's not exposed still has air in the flask. So we're still going to get some oxidation to air regardless of what they do. Suggest how an additional flask could be set up to verify whether the systematic error has occurred. We could do this in a vacuum. Do it in a vacuum. We could use a syringe to inject OJ into flask and fill it. Just some way so that the orange juice is not exposed to the air. We could do this in a chamber of inert gas like argon. Lots of things. All right, the following data is collected during the titration. Calculate the percent uncertainty. So first we need to know how much we actually used. What value did we use? So we're going to take our original minus our final, or sorry, final minus initial to figure out that we used 15.00 centimeters cubed. Our uncertainty was plus or minus 0.05, so that's 5 up and 5 down, or 0.05 up and 0.05 down for a total change of 0.01, or sorry, not 0.01, just 0.1. So we're going to take 0.1 divide by 15.00, multiply by 100 to get a percent, and we'll get 0.67%. All right. For D, the following graph shows the results. Calculate the average rate of decrease in ascorbic acid concentration for the 24-hour period. Well, what I'm just going to do is calculate a slope from my 2 points. I have about 1.1 minus 5.3 for our concentration, divided by 14 minus 0 for our time in days to get a total of 4.2 change over 14 days, which gets me a grand total of 0.30, and I'm going to add back my units, times 10 to the minus third mole decimeter to the negative 3 divided by days. So that is my rate of decrease over the days, over the time. Student's hypothesis is a lower ascorbic acid concentration will be found in the juice exposed to the air for longer due to oxidation of ascorbic acid by oxygen. Discuss whether or not the data supported the hypothesis. It did. Yes, it supports. And then we have to say why. So we have to reference our data. Well, the 24-hour mark had the lowest ascorbic acid, the 0 mark had the highest ascorbic acid, and the others fell into place right in between. So, yes, it supports. The samples that were exposed to air longer had less ascorbic acid. All right, state the implications of the results of the experiment for avoiding loss of vitamin C in storage of orange juice. So this tells us that we want to reduce contact with air. Reduce contact with air. Keep containers closed, etc. Suggest an extension to the investigation that would generate further recommendations for the storage. Well, fridges have temperature settings, so maybe the temperature effect on rate of ascorbic acid decrease. So those would all be great things to test out. Moving on to paper 2. A monoprotic acid, HX, is found to have the following composition by mass. I want to make note that it is monoprotic. 39.99% carbon. What we're going to do is just assume these are all grams, not percentages, because we assume 100 grams. We're going to divide by the molar mass to get moles, grams per mole, which gives us 3.33 mole. C. We'll take our next one, 6.73 grams hydrogen divided by 1.01 grams per mole hydrogen, which gives me 6.66 mole hydrogen. Lastly, oxygen, 53.28 grams oxygen divided by 16.00 grams per mole gives me 3.33 mole oxygen. When I divide these all by the lowest value, I find that I have 1 carbon, 1 oxygen, and 2 hydrogen. So you might be inclined to write CH2O, but that is incorrect because they said this is a monoprotic acid, monoprotic HX. That means we have 1 H in front, then our acid, so HCHO. Moving on to B, 25 centimeters cubed of a solution containing 1.51 grams of HX is titrated with 0.750 mole decimeter cubed solution of NaOH. The HX aqueous solution is exactly neutralized by 22.30 centimeters cubed of NaOH. Determine the molar mass of HX. So I'm going to use the information that's given and relevant. I see that I have 22.30 of NaOH. Oh, sorry, of NaOH, and I have a molarity for that. So I'm going to take my molarity equation, molarity equals mole over volume, and I'm going to try and get mole because I already have volume and molarity. So mole equals molarity times volume. By doing that, I find that 0.750 molarity divided by my volume in decimeters cubed, 0.02230, gets me a mole value of 0.0167 mole NaOH. That's how much NaOH we use to neutralize our HX. Now, because it's monoprotic, when I take NaOH and I add it to HX, I will generally get H2O plus a salt NaX, you'll notice this is a 1 to 1 to 1 to 1 ratio, meaning if I use 0.0167 mole NaOH, I have 0.0167 mole of HX because it's a 1 to 1 ratio. I want the molar mass, which from our first question on this entire test, we noted that molar mass is grams per mole. Well, luckily for me, I have a gram value right here. I have found a mole value, and I can just divide them. 1.51 grams divided by 0.0167 mole will give me a mole value of 90.42 grams per mole. Would you look at that? I have found the molar mass of HX. All right. And if you just want to be sure, these are grams of HX and that is moles of HX. So I know that I am getting a molar mass for HX. Lastly, state the molecular formula of HX. Well, I know that HX has an empirical formula of HCHO. That empirical formula has a mass of 1 plus 12 plus 1 plus 16, approximately 30 grams per mole. But it needs to be 90.42. So all I have to do is multiply this by 3, and then I get about 90. So that means I have to multiply my empirical formula by 3. It is still monoprotic, so I'm still going to keep 1H in front. But C is going to become 3, this H is going to become 2, and that O is going to become 3. Remember, 2 plus 1 is still 3, so it's C3, oh, sorry, whoops, sorry, I messed this one up. Uh, we should have a total of 5 H's. HC3H, H5, whoops, H5O3, and we have a total of 6 H's. Apologies. All right, so that should be that. Lastly, we have this paper to number 2 to end it off. Hydrochloric acid is an important chemical reagent and industrial chemical. pH probe is placed in a small volume of 0.1 mole per decimeter cube solution of hydrochloric acid. The pH is recorded while a steady stream of distilled water is added. On the axis, sketch graph pH versus volume of water added. Well, we start with our pH being equal to the negative log of 0.10. And we know it's set because it's hydrochloric acid, which fully dissociates into H plus and Cl minus, and that is our original concentration. That gives us an initial pH of 1. As we add distilled water, we're going to dilute that. So maybe we then end up with like pH is equal to 0.01. Or sorry, negative log of 0.01. Negative log of 0.01 when we add 100 milliliters or 100 times the amount. And so as we do that, that pH is then 2. So our pH is going to increase. However, we are starting with an acid. We are not adding base. Therefore, the solution will always be acidic, meaning the pH will never go above 7. So it kind of goes like that. And the more water we add, the less it ends up diluting it. Because, well, this to this is a factor of 10, but to the next one is a factor of 100. Remember, pH is a logarithmic scale, so we get this nice logarithmic curve. All right. The experiment's repeated using 0.10 mole decimeter cubed of NaOH at the same temperature. State the initial pH. Well, because we're using NaOH, I'm going to use POH, which is equal to the negative log. It's the same equation, but of our hydroxide, which is equal to 2. Sorry, I wrote 1. But I know that pH plus POH is equal to 14. Therefore, I can rearrange that to say pH is equal to 14 minus POH. which is equal to 14 minus 2, which is equal to 12. All right, and that is it. I believe that's the end of the test. Yep, that is how you do this whole test. Hopefully this helped, and have a great day or night or whatever.